Good morning, everyone. Today, we are going to question reality, not metaphorically, not philosophically, but scientifically. For the next few hours, we are going to explore the strangest, most successful, and most disturbing theory ever created by human beings, quantum physics. By the end of this lecture, you will no longer look at light the same way. You will not look at matter the same way. You may not even look at yourself the same way, because quantum physics tells us something shocking. Reality is not solid. It is not continuous. It is not even fully determined, and yet it works perfectly. Now let me ask you something simple. What is light? Is it a wave? Is it a particle? For 200 years, scientists were confident they knew the answer. They were wrong. For nearly 300 years, physics seemed complete. It began with one giant figure, Isaac Newton. Newton gave us laws of motion. He explained gravity. He explained planetary motion. He built mechanics. And suddenly, the universe became predictable. If you knew the position of every object, the velocity of every object, you could calculate the future. The universe was like a giant clock. Tick, tick, tick. Then came electricity and magnetism. James Clerk Maxwell unified them into equations, and those equations predicted something beautiful. They predicted waves of electricity and magnetism traveling through space. Light. Light was a wave. Everything seemed solved. Physics professors around 1890 were telling students, there is nothing left to discover. Only small refinements remain. That sentence did not age well. Imagine you heat a piece of iron. First, it glows red, then orange, then white. Scientists tried to calculate how much energy such a hot object emits at different wavelengths. Using classical physics, they derived an equation, but when they plotted it, it predicted infinite energy in ultraviolet frequencies. Infinite energy. That is impossible. This disaster became known as the ultraviolet catastrophe. Classical physics, the pride of science, had predicted nonsense. Enter a desperate physicist. Max Planck. Planck did something radical. He said, maybe energy is not continuous. That sentence is revolutionary. He proposed that energy comes in small packets. Quanta. Energy could only be emitted in multiples of E equals hf, where h is a tiny constant, f is frequency. He introduced what we now call Planck's constant. He did not realize he had just broken classical reality, but he had. Now comes the real shock. Scientists shined light on metal surfaces. They observed that electrons were ejected. Classical prediction. Brighter light should eject more energetic electrons, but experiments showed something strange. If the light frequency was too low, nothing happened. No electrons, no matter how bright the light was. But if the frequency was high enough, even dim light ejected electrons instantly. Instantly, no energy buildup. This violated wave theory completely. Then a young patent clerk in Switzerland looked at this and said, what if light behaves like particles? That patent clerk was Albert Einstein. Einstein proposed, light is made of discrete packets, photons. Each photon carries energy. E equals HIF. Higher frequency leads to higher energy per photon. Suddenly, the experiment made sense. Low frequency light leads to photons too weak. High frequency light to photons powerful enough. This was 1905, the birth of quantum physics. Einstein later received the Nobel Prize for this, not for relativity, for the photoelectric effect. Now we reach the experiment that should disturb you. The double-slit experiment. Fire light through two slits. On the screen behind, you see an interference pattern. That proves light is a wave. But then scientists reduced intensity until photons passed one at a time. One photon, not a wave, one particle. Yet the interference pattern still appeared. Each photon behaved as if it passed through both slits simultaneously. Let me repeat that. One photon behaves like it goes through two paths at the same time. If you try to observe which slit it goes through, the pattern disappears. Observation changes outcome. This is not philosophy. This is experiment. If this doesn't disturb you, you haven't understood it yet. So by 1905, physics was in crisis. Energy was quantized. Light behaved like particles. Particles behaved like waves, and observation affected reality. The clockwork universe of Newton was cracking. In the next hour, we will see how this crack becomes a complete revolution. We will explore wave-particle duality, matter waves, and the equation that says even you have a wavelength. Yes, you have a wavelength. Welcome back. Earlier, we broke classical physics. Energy is not continuous. Light is not just a wave. Observation changes outcomes. Now we go one step further. And this step is even more dangerous. Because in this hour, we will ask, if light, which we thought was a wave, can behave like a particle, then can matter, which we thought was a particle, behave like a wave? If that is true, then you are not just sitting in this chair as a solid object. You are also a wave. Let's begin. By 1905, physics had a split personality. Light behaved like a wave in interference experiments, a particle in the photoelectric effect. So what is it? Wave, particle? Scientists tried to choose one, but experiments kept supporting both. This forced physicists into a painful realization. Nature does not care about our categories. Wave and particle are human words. Reality is something deeper. Then in 1924, a young French physicist asked a bold question. That physicist was Louis de Broglie. De Broglie said something extraordinary. He said, if waves can behave like particles, then particles can behave like waves. He proposed that every particle with momentum has a wavelength. He even derived the formula, lambda equals h divided by p. Let me write it clearly. Lambda equals h over p, where lambda is wavelength. H is Planck's constant, p is momentum. Momentum is mass times velocity. So lambda equals h over mv. This equation is simple, but its consequences are enormous. 40 minutes to 55 minutes. What does this mean? Let's test this idea. Suppose we take a cricket ball. Mass 0.15 kilograms, velocity 30 meters per second. Calculate its wavelength using lambda equals h over mv. Planck's constant is extremely tiny, 6.626 times 10 to the minus 34. When you calculate this, the wavelength is unimaginably small, far smaller than atomic size. That's why we never see cricket balls behaving like waves. But now let's shrink the mass. Take an electron. Mass, about 9.11 times 10 to the minus 31 kilograms. Now calculate its wavelength at reasonable speeds. Suddenly the wavelength becomes comparable to atomic dimensions. That means electrons can show wave behavior, not theoretically, experimentally. In 1927, two physicists tested this idea. They fired electrons at a crystal. Classically, electrons are particles, so they should scatter randomly. Instead, they produced an interference pattern, exactly like waves diffracting through a crystal lattice. The experiment confirmed de Broglie's idea. Electrons behave like waves. This experiment was performed by Clinton Davison and Lester Germer. Matter was not solid little balls. It had wave properties. That means the chair you are sitting on is made of wave-like entities. Now comes the truly shocking part. Scientists repeated the double-slit experiment, but this time with electrons. They fired electrons one at a time. One electron, wait, another electron, wait, another. Each electron hit the screen as a single dot, but over time, the dots formed an interference pattern, meaning each electron interfered with itself, as if it passed through both slits at once. Think about that carefully. One electron, two paths. If we place detectors to check which slit it goes through, the interference disappears. The electron behaves like a particle. If we do not observe, it behaves like a wave. Observation changes reality. This is not mystical. It is measurable. It is repeatable. It is real. Let us summarize. Light, wave in some experiments. Particle in others. Electrons, particle in some experiments. Wave in others. Conclusion. Every quantum object is both. We call this wave-particle duality. But that phrase is misleading. It is not half wave, half particle. It is something deeper that appears wave-like or particle-like, depending on how we measure it. Reality depends on interaction, not on fixed properties. This destroys classical determinism. In classical physics, objects have definite positions and velocities. In quantum physics, properties emerge when measured. In the few minutes, we will go deeper. We will discuss a principle that limits knowledge itself, a principle discovered by Werner Heisenberg, the uncertainty principle. And once you understand it, you will realize that uncertainty is not a weakness of science. It is a law of nature. Take a break. When we return, we confront uncertainty. In the last few minutes, we discovered something unsettling. Electrons behave like waves. Particles interfere with themselves. Observation changes outcomes. Now we go deeper. Let me ask you something simple. If I give you a ball, can you measure its position, its velocity? Of course. And if your instruments are good enough, you can measure both very precisely. Classical physics assumes something powerful, that position and velocity both exist simultaneously with exact values. Even if you don't measure them, quantum physics disagrees. And the man who proved it was Werner Heisenberg. What he discovered was not a technological limitation, not a measurement error, but a fundamental law of reality. And that law says, the more precisely you know where something is, the less precisely you can know how fast it is moving. Let me write the equation. Delta x times delta p is greater than or equal to h divided by 4 pi, where delta x is uncertainty in position, delta p is uncertainty in momentum, h is Planck's constant. This equation is not optional. It is not experimental error. It is a built-in feature of the universe. Why should nature behave like this? The answer lies in waves. Remember, electrons are not tiny balls. They are wave-like entities. Now think about a wave. If I have a perfect sine wave extending infinitely in space, it has a perfectly defined wavelength, which means perfectly defined momentum. But can you say exactly where it is located? No, it is everywhere. Now suppose I try to localize it. I combine many waves of different wavelengths. This creates a wave packet. Now it is localized in space. But because I combined many wavelengths, its momentum becomes uncertain. This is not philosophy. It is mathematics. Localization in space requires mixing momenta. Therefore, precise position implies uncertain momentum. Precise momentum implies uncertain position. This is wave behavior, and matter behaves like waves. Many students misunderstand this. They think, maybe our instruments disturb the particle. That is partially true, but not the full story. Even if you had a perfect measuring device, even if no disturbance occurred, the uncertainty principle would still apply. Why? Because particles do not possess exact simultaneous position and momentum. They possess probability distributions. This is the radical shift. In classical physics, objects have properties. In quantum physics, objects have probability amplitudes. Nature is not hiding information from us. The information does not exist in the classical sense. Imagine trying to locate an electron. To see something, you must shine light on it. If you use long wavelength light, it barely disturbs the electron, but the wavelength is large, so your position measurement is blurry. If you use short wavelength light, you get better position precision. But short wavelength means high frequency. High frequency means high energy. High energy photon hits the electron hard. Its momentum changes unpredictably. Either way, precision in one destroys precision in the other. This is sometimes called the gamma-ray microscope thought experiment. But remember, the deeper reason is wave nature. Now we reach something philosophical. In Newton's universe, if you know position and velocity exactly, you can predict the future exactly. That is determinism. But quantum mechanics says exact position and exact momentum cannot coexist. Therefore, exact prediction of future trajectories is impossible. Not practically impossible, fundamentally impossible. The universe at its core is probabilistic. This disturbed many physicists, including Albert Einstein. Einstein famously said, "God does not play dice." Quantum mechanics replied, "Yes, he does." Let us summarize. Matter behaves like waves. Waves cannot be localized without spreading momentum. Therefore, uncertainty is built into reality. The uncertainty principle is not about ignorance. It is about the structure of existence. This means the future is not a fixed script. It is a range of probabilities. And to calculate those probabilities, we need a new equation, an equation that governs how these wave-like entities evolve in time, an equation discovered by Erwin Schrödinger. In the next few minutes, we write the most important equation in quantum mechanics, the Schrödinger equation. Next, we stop talking about ideas and start writing the mathematics of reality.
So far, we have broken classical physics. We have seen that light behaves like particles. Matter behaves like waves. Position and momentum cannot both be precise. Now we ask the most important question. If matter behaves like waves, what equation governs those waves? For water waves, we have wave equations. For sound waves, we have equations. For electromagnetic waves, we have Maxwell's equations. So what is the equation for matter waves? In 1926, a physicist found it. His name was Erwin Schrödinger, and the equation he discovered changed physics forever. I will now write the equation. Do not panic. Look at it calmly. I h bar partial, psi over partial, t equals h hat psi. This is the time-dependent Schrödinger equation. Let's decode it slowly. Psi is the wave function. H bar is h divided by 2 pi. H hat is the Hamiltonian operator. I is the imaginary unit. Yes, imaginary numbers are part of reality. That alone should make you pause. What is psi? Is it a physical wave like water? No, it is more abstract. The wave function contains all information about a quantum system. But here is the subtle part. Psi itself is not directly observable. What we measure is the absolute value of psi squared, the square of its magnitude, and the absolute value of psi squared gives probability density. This interpretation was clarified by Max Born said, "The wave function does not describe a solid object, it describes probability." This is revolutionary. In classical physics, we calculate trajectories. In quantum physics, we calculate probabilities. Let's simplify everything. Imagine a particle trapped between two rigid walls. It cannot escape. Classically, it could have any energy. Quantum mechanically, it cannot. When we solve Schrödinger's equation for this system, we find something shocking. Only certain energy levels are allowed. Energy becomes quantized naturally, not assumed, derived. The allowed energies depend on the mass of the particle, the size of the box. Planck's constant and the wave function forms standing waves inside the box, just like a guitar string, but instead of sound, we get quantized energy. This explains why atoms have discrete spectral lines, because electrons inside atoms can only occupy certain energy states. Let's step back. What does the Schrödinger equation really say? It tells us how the wave function evolves over time. It does not tell us the particle is here. It tells us there is a probability of finding the particle here. This shift is enormous. Reality at microscopic scales is not deterministic. It evolves according to probability amplitudes. But here's the strange part. The equation itself is completely deterministic. If you know psi at one moment, you can calculate psi at any future moment. So where does randomness enter? It enters during measurement. The equation evolves smoothly. Measurement causes collapse. This is where quantum mechanics becomes mysterious. The Schrödinger equation allows superposition. If psi1 is a solution and psi2 is a solution, then any combination, a psi1 plus b psi2, is also a solution. That means a particle can exist in multiple states simultaneously, not one or the other. Both. Until measured. This is not metaphorical, it is mathematical. Let us summarize this topic. The Schrödinger equation governs quantum systems. The wave function describes probability amplitudes. Energy levels become quantized naturally. Superposition is built into the mathematics. Now we are ready for something deeply unsettling. If superposition is real, what happens when we apply it to everyday objects? What happens if something is both alive and dead? In the next hour, we explore Schrödinger's cat and the interpretation of quantum mechanics.
Earlier, we wrote the Schrödinger equation. We learned that the wave function evolves smoothly. Energy becomes quantized. Superposition is mathematically allowed. Now we ask the dangerous question, if an electron can exist in multiple states at once, why don't we see cats in multiple states? Why don't we see chairs in two places? Why doesn't the world look blurry and probabilistic? To expose this problem, Schrödinger invented a thought experiment, and it became the most famous paradox in physics. The physicist who proposed this was Erwin Schrödinger. Here is the setup. Imagine a sealed box. Inside the box, a cat, a tiny amount of radioactive material, a detector, a vial of poison. If the radioactive atom decays, the detector triggers, the vial breaks, the cat dies. If the atom does not decay, the cat lives. Now here's the key. Radioactive decay is a quantum event. Before measurement, the atom is in a superposition of decayed, not decayed. If the atom is in superposition, then the detector is in superposition. Then the poison is in superposition. Then the cat is in superposition, alive and dead, simultaneously. According to the Schrödinger equation, until we open the box, the cat is both alive and dead. This sounds absurd, and that was Schrödinger's point. He was criticizing quantum mechanics. The dominant interpretation at the time was developed by Niels Bohr. This is called the Copenhagen interpretation. It says the wave function represents all possible outcomes, but when measurement occurs, the wave function collapses into one definite result. Before measurement, the system exists in superposition. After measurement, only one outcome remains. The act of measurement selects reality, not because consciousness creates reality, but because interaction with the environment forces a definite outcome. Now we must ask, what counts as a measurement? Is it a human observer? Is it a machine? Is it any interaction? Modern physics suggests any irreversible interaction with the environment can cause collapse. This leads to the concept of decoherence. When a quantum system interacts with millions of particles in its environment, superposition becomes effectively unobservable. That is why we do not see macroscopic superpositions. The world appears classical because of constant environmental interaction. The cat is not visibly alive and dead because it is interacting with air molecules, photons, thermal vibrations. Superposition becomes hidden. This debate disturbed many physicists, including Albert Einstein. Einstein believed quantum mechanics was incomplete. He believed there must be hidden variables, something deeper determining outcomes. Bohr disagreed. He argued quantum mechanics is complete. Probability is fundamental. Their debates were legendary. Einstein said, "God does not play dice." Bohr replied, "Stop telling God what to do." Not everyone accepted collapse. Some alternatives emerged. One radical idea, the many worlds interpretation, proposed by Hugh Everett. It says the wave function never collapses. Instead, the universe splits. When the box is opened, one universe contains a live cat. Another universe contains a dead cat. Both are real. You experience only one branch. This interpretation removes collapse, but multiplies reality. In this view, there are countless versions of you, branching every second. Let us summarize this hour. Superposition is mathematically real. Schrödinger's cat exposes the paradox. Copenhagen says collapse occurs during measurement. Many worlds says collapse never occurs. Quantum mechanics works perfectly in prediction, but its meaning remains debated. We now move to something even more unsettling: entanglement. Two particles connected across space, so deeply connected that measuring one instantly affects the other. Einstein called it spooky action at a distance. In the next few minutes, we explore quantum entanglement. Take a break. When we return, space itself becomes questionable. Welcome back. So far, we have accepted particles behave like waves. Properties exist as probabilities. Measurement affects outcomes. Superposition allows multiple possibilities at once. Now we ask a new question. What happens if two particles interact and then separate? Classically, once they separate, they are independent. Quantum mechanically, they may remain connected, not by a force, not by a signal, but by a shared wave function. This phenomenon is called entanglement. Imagine two electrons created together in a way that conserves spin. One must be spin up, the other must be spin down. But quantum mechanics says
Before measurement, each electron is not definitively up or down. The pair exists in a superposition, up, down, and down, up simultaneously. Now we separate them. Send one to Dubai, send the other to New York. They are now thousands of kilometers apart. We measure the first electron. Suppose we find it spin up. Instantly, the second electron becomes spin down. Instantly, no delay, no signal traveling between them, just immediate correlation. This is entanglement. It sounds impossible, but experiments confirm it. In 1935, 3 physicists challenged quantum mechanics. They were Albert Einstein, Boris Podolsky, Nathan Rosen. Together they proposed what is now called the EPR paradox. They argued, if measuring one particle instantly determines the other, then either information travels faster than light, or the particles carried hidden instructions all along. Einstein preferred the second option. He believed quantum mechanics was incomplete. He called entanglement spooky action at a distance, and he disliked it intensely. For decades, this debate was philosophical. Then in 1964, a physicist named John Bell changed everything. Bell derived an inequality, a mathematical test. He showed, if hidden variables exist, then certain statistical limits must hold. If quantum mechanics is correct, those limits will be violated. This was testable. Physics moved from philosophy to experiment. In the 1980s, experiments were performed, most famously by Alain Aspect. They measured entangled photons, and what did they find? Bell's inequality was violated. Nature does not obey local hidden variables. Einstein was wrong about this. Quantum mechanics was correct. Entanglement is real. 2 particles can share a single quantum state. Distance does not break the connection. Now a crucial question. If the second particle responds instantly, is faster than light communication possible? No. Why? Because although the results are correlated, each individual measurement is random. You cannot control the outcome. Therefore, you cannot send information faster than light. Relativity survives, but locality does not. The universe is non-local at a fundamental level. Let us summarize this topic. Entangled particles share a joint wave function. Measuring one instantly determines the other. Bell's theorem ruled out local hidden variables. The universe is fundamentally non-local. This is not science fiction. It is experimentally verified. And entanglement is not just philosophical, it is useful. In the next few minutes, we explore applications of quantum mechanics, transistors, lasers, MRI machines, modern electronics, and eventually quantum computers. Next, we discuss how quantum physics becomes practical. So far, quantum mechanics has sounded mysterious. Waves behaving like particles, cats both alive and dead, particles connected across continents. It may feel abstract, but here is something important. Without quantum mechanics, modern civilization would collapse. No smartphones, no laptops, no MRI machines, no lasers, no modern electronics. Quantum mechanics is not philosophical decoration. It is the engine of the 21st century. Let us begin with the most important invention of modern technology, the transistor. Transistors are made from semiconductors like silicon. To understand semiconductors, we must use quantum mechanics. In atoms, electrons occupy discrete energy levels. In solids, these levels form bands: valence band, conduction band. Between them is an energy gap. Quantum mechanics explains why this gap exists. By carefully adding impurities, a process called doping, we control electron flow.
This control allows switching. Switching allows logic. Logic allows computation. Every microprocessor in your phone contains billions of transistors, and every transistor works because of quantum mechanics. You are holding quantum physics in your pocket. Next, the laser. Laser stands for light amplification by stimulated emission of radiation. The key concept is stimulated emission. This was predicted by Albert Einstein in 1917. Here is how it works. An atom absorbs energy. An electron jumps to a higher energy level. Eventually, it falls back down. When it does, it emits a photon. If a photon of the right energy passes by, it can stimulate the excited atom to emit another photon. Both photons, same energy, same direction, same phase. This produces coherent light, that is laser light, used in fiber optics, surgery, barcode scanners, military systems, eye correction, all based on quantized energy levels. Next, MRI, magnetic resonance imaging. This technology relies on quantum spin. Protons inside hydrogen atoms behave like tiny magnets. When placed in a strong magnetic field, their spins align. Radio waves disturb this alignment. When spins relax back, they emit signals. These signals are detected and converted into images. This is quantum mechanics inside your hospital. Your brain scan depends on spin states. Now something even stranger, quantum tunneling. Classically, if a particle does not have enough energy to cross a barrier, it cannot cross. Quantum mechanically, there is a probability it appears on the other side. It tunnels through. This is not metaphorical. It is measurable. Tunneling is used in flash memory, scanning, tunneling microscopes, nuclear fusion inside stars. Yes, the sun shines because of quantum tunneling. Without tunneling, protons in the sun would not overcome their electric repulsion. The stars themselves rely on quantum probability. Quantum mechanics eventually evolved into quantum field theory. In this framework, particles are excitations of fields. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. This structure forms the standard model of particle physics. Much of this research happens at CERN, where high-energy collisions probe fundamental particles. Quantum theory predicted the Higgs boson decades before it was detected, and in 2012, it was finally observed. Let us summarize. Quantum mechanics gave us transistors, lasers, MRI tunneling devices, particle physics, modern electronics. The strange mathematics we studied built the modern world, and yet we are only at the beginning, because quantum mechanics is not just about explaining nature, it is about controlling it. In the next few minutes, we explore quantum computing, qubits, superposition as a resource, entanglement as computational power, and why the next technological revolution will be quantum. Take a break. When we return, we step into the future. Welcome back. So far, quantum mechanics has helped us build transistors, create lasers, understand atoms, explain stars. But now we ask a bigger question. What if we stop fighting quantum weirdness and start using it directly? What if superposition becomes a tool? What if entanglement becomes computational power? This is the idea behind quantum computing. And if it succeeds, it will transform technology more dramatically than the invention of the transistor. In classical computing, the basic unit is a bit. A bit can be 0 or 1. Everything, text, images, videos, reduces to combinations of zeros and ones. Now imagine a quantum bit, a qubit. A qubit can be 0, 1, or a superposition of 0 and 1. Mathematically, psi equals alpha 0 plus beta 1, where alpha and beta are complex probability amplitudes. Alpha squared plus beta squared equals 1. This means the qubit is not simply one or the other. It is both, simultaneously, until measured. Now imagine one classical bit, two possible states, with two classical bits, four possible combinations, with three classical bits, 8 combinations. It grows linearly in storage, but with quantum bits, 2 qubits can exist in a superposition of 4 states simultaneously. 3 qubits, 8 states simultaneously. N qubits, 2 to the power of n states at once. This exponential growth is extraordinary. A quantum computer with 300 qubits could represent more states than atoms in the observable universe. That is the power of superposition. But representation is not enough. We need control. Now we add entanglement. When qubits become entangled, their states cannot be described independently. Operations on one affect the other. This allows quantum algorithms to explore multiple computational paths simultaneously. One famous example is Shor's algorithm. It can factor large numbers exponentially faster than classical algorithms. Why does this matter? Because modern encryption relies on factoring being hard. If large-scale quantum computers are built, much of today's encryption would break. This is why governments invest heavily in quantum research. Quantum computers already exist. Companies and research labs build machines using superconducting circuits, trapped ions, photonic systems. Superconducting qubits operate at temperatures near absolute zero. Why? Because heat destroys quantum coherence. Maintaining superposition is extremely fragile. The biggest challenge in quantum computing is decoherence. The environment constantly tries to collapse the wave function, so engineers must isolate qubits from noise. Quantum error correction is a major research field. The race is on. Quantum mechanics also enables new forms of communication. Quantum key distribution allows two parties to detect eavesdropping automatically, because measuring a quantum state disturbs it. If someone intercepts the key, the disturbance reveals their presence. This is already used in secure communication systems. Quantum teleportation has also been demonstrated, not teleporting matter, but teleporting quantum states using entanglement. The future internet may be quantum. Let us summarize. Qubits use superposition. Entanglement enables exponential computational power. Quantum machines already exist. The future of encryption and communication may be quantum, but major questions remain. Can we scale quantum computers reliably? Can we unify quantum mechanics with gravity? Is there a deeper theory beyond quantum mechanics? After this lecture, you now understand. Quantum physics is not mystical nonsense. It is mathematically precise, experimentally verified, technologically transformative. In the final few minutes, we step back. We ask the deepest question of all. What does quantum mechanics say about reality itself? Is the universe fundamentally probabilistic? Are there many worlds? Is information more fundamental than matter? In next few minutes, we conclude this journey.
For last few minutes we have explored the failure of classical physics, wave-particle duality, the uncertainty principle, the Schrödinger equation, superposition, entanglement, modern technology, quantum computing. Now we stop calculating. Now we ask, what does all this mean? What is reality according to quantum mechanics? Is the universe deterministic? Is it probabilistic? Does observation create reality? Or is there something deeper? Physics began as a search for certainty.
Quantum mechanics gave us probability. In classical physics, probability meant ignorance. If I flip a coin and I don't know the outcome, that's because I lack information. But the coin itself has a definite state. Quantum mechanics says something more radical. Before measurement, the system does not possess a definite classical property. It exists in a superposition. Probability is not ignorance. It is fundamental. This is deeply uncomfortable. It means the universe is not a rigid script. It is a cloud of possibilities. Physicists still debate what quantum mechanics truly means. Let us review the major interpretations. First, the Copenhagen interpretation, associated with Niels Bohr. It says the wave function is complete. Collapse occurs upon measurement. Questions about unobserved reality are meaningless. Second, many worlds, proposed by Hugh Everett. It says the wave function never collapses. Every possible outcome occurs. The universe branches continuously. Third, pilot wave theory, originally suggested by Louis de Broglie and later developed by David Bohm. It says particles have definite positions. A hidden guiding wave determines motion. Determinism is restored, but non-locality remains. Each interpretation reproduces the same experimental predictions, but they describe different realities. Quantum mechanics is mathematically clear. Its meaning is not. Some physicists propose something radical. Maybe matter is not fundamental. Maybe information is. Quantum states encode information. Black hole physics suggests information cannot be destroyed. Some propose the universe is a quantum information processing system. Reality may be fundamentally informational. This idea connects quantum physics with computation. Now we approach a sensitive topic. Does consciousness play a role? Early debate sometimes suggested that observation by a conscious mind collapses the wave function. However, modern physics does not require consciousness. Measurement is interaction. A detector collapses a wave function without awareness. We must be careful not to mix physics with mysticism. Quantum mechanics is strange enough without adding unsupported claims. One major problem remains. Quantum mechanics describes the small. General relativity describes gravity and space-time, but they do not fully agree. We still lack a complete theory of quantum gravity. Attempts include string theory, loop, quantum gravity, but no final answer yet. This is one of the greatest open questions in physics. Let us reflect on what we have learned today. At the smallest scales, matter is not solid. Properties are probabilistic. Particles can be entangled across distance. Reality depends on interaction. And yet, the theory works with astonishing precision. Quantum electrodynamics predicts experimental results to extraordinary accuracy. The most successful theory in science is also the strangest. Perhaps the lesson is this: nature is not obligated to be intuitive. It is obligated only to be consistent. After this lecture, you now understand the intellectual revolution of the 20th century. You have seen the collapse of certainty. You have seen probability replace determinism. You have seen that the universe is far stranger than common sense, and yet it is deeply beautiful.